Okay, morning everyone. Boleh tak update dengan madam you punya schedule dengan technician bila eh? You dengar tak suara saya?
Dengar ni dia.
Okay, boleh tak update besok? Because saya nak create attendance dalam e-learning nanti schedule tu. As attendance lah. Okay. Okay, so hari ni saya tak sempat lagi buat rakaman kelas because ada isu sikit lagi pasal special exam Okay, so hari ni saya akan cover briefing untuk not sure lah, maybe kalau sempat 4 experiments So we'll start here dekat experiment number 3. Okay, on the Bernoulli Bernoulli. So this one, saya brief dulu the steps or the procedure. Okay, so untuk third experiment on the Bernoulli's theorem. Okay, so the course outcome is to verify the principle of fluid mechanics. So I think you all are familiar about this principle, right? Fluid mechanics, because this is the prerequisite for the subject, kan? Okay. So the main objective is to investigate the flow rate using particular flow measuring apparatus. For this demonstration, there are two sub-objectives. First one, to demonstrate the variation of the pressure along a converging diverging pipe sections, and second one is to investigate the validity of the Bernoulli equations when applied to the steady flow of water in the tapered duct. Okay, so the concept ataupun teori for the third experiment will be based on this one lah. Flow remains constant along a streamline. So this theory is represented by these equations. Okay, so there are meaning behind this symbol. The small p symbol means static pressure detected at a side hole. Small v is the velocity, okay, for the fluid. Z is the vertical elevation of the fluid. Z1 and Z2 is the horizontal tube. Okay. Okay, Z1 is equal to Z2 or a horizontal tube. Okay, so this equation ataupun this equation yang atas ni, okay, to describe about the Bernoulli's theorem, it can be derived from Euler equation lah by using integration. That means kalau kita integrate Euler equation, you can get lah equation atas. Okay. It also can be derived from energy conservation principle, and for the experiment macam mana nak derive here, kita tak cover lah. Basically, that one is more into those are in the mathematical field lah. Degree in maths that, so that then you need to know how to derive. Okay, so as an engineering student, you should know how to apply and what kind of equation that is required for you to apply according to the concept. Okay, and then in the above equations, for that case, if the tube is horizontal, then the difference between the height can be disregarded. In other words, kalau case for this tube as horizontal, so you have case yang Z1 sama dengan Z2. Kalau dia bukan horizontal, that means it's not equal lah. Okay, these two. So the above equation you can rewrite lah into this form. And then with the apparatus, the static pressure head P is measured using a manometer directly from a side hole pressure tapping, and this measure the static pressure head. Okay, so static pressure head labeled by H, unit in meters. Okay, SI unit as in meter, which is related to P using this relationship. Okay, H punya equation. So that means from the previous equation, you can rewrite into another form lah. So in another form, you can have this kind of equations lah. Okay, so equation yang baru ni is known as the velocity related portion of the total pressure is called dynamic pressure head. Okay, so this concept lah. So that means dynamic pressure head can be derived, can be described based on these equations lah. Okay, and then we have total pressure head. So this is the important terms in this fluid mechanics. The total pressure head that is denoted by H here can be measured from a probe with an end hole facing into the flow such that it brings the flow to rest locally at the probe end. So that means you have this kind. So degree at this H is equal to here H plus V squared over 2J. The unit is in these kinds of units in meter, and from the Bernoulli equation, because this H relate to your punya Z kan, so you have these kinds of situations lah. H1 degree is equal to H2 degrees. Okay, the next important term that you should know is about the velocity measurement. Okay, the velocity is represented by this capital V. Okay, it's it is known as volume of the flow over a time of period t. So the time is unit is t, symbol t. So that means the rate of volume flow as is given as this equation. QV is equal to capital V divided by t, which in turn give the velocity of flow through some defined area. Okay, maksud defined area means that you should know lah that area tu is some kinds of mentions ataupun defined area. Means that you exactly know what kinds of area yang covered. Kalau you are not sure that area is covered to which region, then it's not called as defined area lah. Okay, so rate of volume is given by this equation, QV divided by A. Okay. Okay, next is continuity equations. Okay, continuity equation you can see when you have incompressible fluid. Conservation of mass requires that the volume is also conserved. Okay, that means you have these kinds of situations. A1 times V1 is equal to A2 times V2. So A means the area or defined area. V1 is you punya velocity of the flow lah. Okay. Okay. So the setup for this experiment number 3, okay, to demonstrate the Bernoulli's theorem, you must have this hydraulic bench. Okay, so it is to measure flow lah by time collections, volume collections, and then the test equipment on this Bernoulli's and a stopwatch. Okay, so you can see in this figure. Okay, so again here, madam not sure lah whether these tools is in the lab. Nanti you can refer to technicians lah. Okay. Okay. For that one, the test section is accurately machined, clear acrylic duct of varying circular cross sections. It's provided with a few side hole pressure tappings, which are connected to the manometers housed on the rig. Okay, so these tappings allow the measurement of static pressure head simultaneously at each of 6 sections. Okay, so 6 sections ni measured lah you punya tapping positions where you can see the detail of the dimensions of the tube given lah in as shown here. So we have first column including the tapping positions, then the manometer legend, then the diameter lah for that each positions. Okay. And you have what converging to diverging pipe. See, you can see this figure. Have you ever seen about this converging diverging pipe in previous subject? Ada jumpa tak? Which subject?
Macam fluid mechanics ni yang apa tu? Yang pipe.
Fluid mechanics lah.
Hmm.
Okay. So madam boleh tanya lah, converging tu kat bahagian mana? Diverging tu kat bahagian mana? Ingat tak?
converging tu rasanya dekat bahagian yang makin mengecil.
Betul. Dia macam semakin kecil tu dia converging lah. Kalau macam saluran tu membesar, semakin membesar is for the diverging. Okay, so that's why dia panggil this a converging and diverging pipe. Okay, so the procedure for the demonstrations, reading should be taken at 3 flow rates. And then for the first reading, for the maximum flow rate, and then reduce the volume flow rate to give the H1 to H5 heat difference of about 50 millimeter. Okay, so that means you ada heat difference daripada H1 to H5 increase, okay, ataupun lebih decrease by 50 millimeter, and then repeat the process for one further flow rate. Okay, set to give the H1 to H5 heat difference approximately halfway between the obtained in the above two sets. Okay, then for the H1 to H5 manometers, take the readings. When the levels have steadied, make sure the total pressure probe is retracted from the test sections. And then time volume collections, close the ball valve and measure with a stopwatch, okay, to accumulate volume of fluid in the tank. And then measure the total pressure heat distribution by traversing the total pressure probe along the length of the test sections. The datum line is the side hole pressure tapping associated with a manometer H1. Okay, make sure that a suitable starting point is 1 centimeter upstream of the beginning of the 14-degree tapered sections, and measurements should be made at 1 centimeter intervals. That means that you do the measurements within the 1 centimeter interval along the test sections length until the end of the divergent 21-degree sections. Okay, ensure the total pressure probe is fully withdrawn from the test sections. Okay, and then unscrew the two couplings, remove the test sections and reverse it. Then reassemble by tightening the coupling. Okay, so what to do, or what you are supposed to collect for the data or show the data presentations. Okay, so in table, calculate and plot relevant graph to show, for example, graph regarding relationship between P and the distance. Okay, and then the raw data should be taken in terms of, let's say, you punya H1, H2 and other items that I have explained or symbols before this. Okay, and then observe the relationship. Once you have graph, later on your graph you need to make some summary ataupun descriptions lah. Okay, outcome from the graph, what kinds of the relationship, whether they have positive or negative relationship. Okay, that means positive relationship means that maybe kalau pressure heat is increased, dynamic heat, the measurement on the dynamic heat also increase. Or you can have, if one variable is decreased, the other variable is also decreased, then you have also another positive relationship. But if they have vice versa, one is increased, the other one is decreased, that means you have negative relationship. So that kinds of relationship should be mentioned lah, okay, in your report. Okay, and then please state the comparison of the total heats obtained by the two methods you have carried out. So after you present your data collections and you punya raw data, discuss and then interpret the results. Okay, and then end by you punya recommendations lah, how to improve the error while doing the experiments. Okay, so do you have any questions about this Bernoulli theorem?
No madam.
Tak ada meja.
Tak ada. Okay, so madam free.
Madam nak tanya, next week punya class still online ke atau dah start physical dah?
Next week online, tapi I think sebab cuti raya kan, jadi tak pasti.
Alright.
Biasa sebab next week kebanyakannya akan cuti.
Okay lah.
Kenapalah banyak sangat iklan.
The Bernoulli equation
Boleh dengar sound kan?
Boleh ni.
Boleh.
is an important relation in fluid mechanics since it expresses the relationship between fluid pressure, velocity, and elevation for an incompressible fluid along a streamline. Bernoulli's theorem is based on four assumptions for fluid flow: frictionless, steady, incompressible, and along the same streamline. The test section is an accurately machined clear acrylic duct of a varying circular cross-section. It is provided with a number of side hole pressure tappings which are connected to the manometers housed on the rig. These tappings allow the measurement of static pressure heads simultaneously at each of the 6 sections. The test section incorporates 2 unions, one at either end to facilitate reversal for convergent or divergent testing. A hypodermic probe is provided which may be positioned to read the total pressure head at any section of the duct. This total pressure head probe may be moved after slackening the gland nut. This nut should be retightened by hand. All 8 pressure tappings are connected to a bank of pressurized manometer tubes. Before starting the experiment, set up the Bernoulli equation apparatus on the hydraulic bench so that the base is horizontal.
Ensure that the test section has the 14-degree tapered section converging in the direction of flow. If you need to reverse the test section, the total pressure head probe must be withdrawn before releasing the mounting couplings. Ensure that the rig outflow tube is positioned above the volumetric tank. Connect the rig inlet to the bench flow supply. Close the bench valve and the apparatus flow control valve to start the pump. Gradually open the bench valve to fill the test rig with water.
In order to bleed air from pressure tapping points and manometers, close both the bench valve, the rig valve, and open the air bleed screw. Now open the bench valve and allow flow through the manometers to purge all air from them. Then tighten the air bleed screw and partially open the test rig flow control valve. Next, open the air bleed screw slightly to allow air to enter the top of the manometers. You may need to adjust both valves in order to achieve this. Retighten the screw when the manometer levels reach a convenient height. This maximum volume flow rate will be determined by the need to have the maximum H1 and minimum H5 manometer readings both on scale. Readings should be taken at 3 flow rates. Take the first set of readings at the maximum flow rate possible with all manometers reading on the baseboard. Then reduce the volume flow rate to give the H1 through H5 head difference of about 50 millimeters. Finally, repeat the whole process for one further flow rate set to give H1 to H5 difference approximately halfway between that obtained in the above 2 tests.
Take readings of the H1 to H6 manometers when the levels have steadied. Ensure that the total pressure probe is retracted from the test section. You should carry out a timed volume collection using the volumetric tank in order to determine the volume flow rate. This is achieved by closing the ball valve and measuring with a stopwatch the time taken to accumulate a known volume of fluid in the tank, which is read from the sight glass. You should collect fluid for at least 1 minute to minimize timing errors.
Measure the total pressure head distribution by traversing the total pressure probe along the length of the test section at points A to F. The datum line is the side hole pressure tapping A associated with manometer H1. Finally, you may reverse the test section in order to see the effects of a more rapid converging section. Ensure that the total pressure probe is fully withdrawn from the test section but not pulled out of its guide in the downstream coupling. Unscrew the 2 couplings, remove the test section and reverse it, then reassemble by tightening the coupling. Repeat the set of readings as before.
Be sure to clean up your station and any water that may have spilled. Following the lab manual, complete the results table and put together your lab report. If you have any questions, consult your teaching assistant or professor.
YouTube Music is a music app made by YouTube and it's your key.
Okay, medium play ada satu lagi video kejap.
New SK2 #1 Brightening Essence. Clear stubborn dullness. Unleash your ultimate aura from inside out.
Assalamualaikum and a very good morning. We are from Group 1 and today we'll be doing Bernoulli's theorem demonstration. This is the general startup. First of all, you have to make sure that the power supply is on. Next, you have to make sure that the valve is fully closed. Then, when you have made sure, you can turn on the switch. You can then open the valve and fill the water in the tube. Ensure there's no air bubble. When you're sure there's no air bubble, you can close the valve and turn off the switch. Then, lower the water level until at least half. Then we will have to wait for the level to stabilize. You can wait at least for 10 to 15 minutes. Okay, this is the first part of the experiment, which is the discharge coefficient determination. The objective of this experiment is to determine the discharge coefficient of the venturimeter. First of all, you have to turn on the switch, open the valve just a little bit so that there will be difference in the water level. When water level is stabilized, you can then measure the difference in pressure using the venturimeter. You have to measure each and every point, make sure that it's in the middle, and then you take the readings. After doing that for every point, you can then calculate the flow rate. First of all, you have to close the hole. And then then you have to take your time when the water level is at 0 and stop when it's reached 3. And then you can calculate the volume and the volume and the time so that you can get the flow rate. For the second part of the experiment, the objective is to measure flow rate with venturimeter. Repeat the same step until step 4. Then, calculate the venturimeter flow rate of each data by applying the discharge coefficient obtained from the first part and compare it with the venturimeter flow rate. For the third part of the
dengan Rexona 3X Law untuk kekeringan, kesegaran dan wangian tahan lama dalam apa keadaan sekalipun.
Okay. Okay. Ada soalan tak pasal eksperimen tadi?
Saya okay, betul.
Okay, kejap kejap, hari tu timetable kan Roshini inform saya jadual you clash kan dengan subjek miss. So macam mana
Oh, yang tu tak clash pada sebab dia student dia drop dah.
Student drop. Okay.
Sudah tukar waktu dah.
Sebab masa last week saya dah terus free attendance pukul 12. So kita nak pukul 11 pukul 12.
Okey kot je. Okey je, ikut madam lah. Sebab tu kelas MNE, lepas tu semalam baru Sir Faisal discuss nak tukar Isnin tapi tak sure waktu lagi. Sebab tu kelas 3 jam, so kalau madam buat pukul 12, so saya nak buat 9 sampai 12 pun okey juga untuk kelas MNE.
Yang hari Selasa ni.
Oh, Selasa tak ada clash madam?
No, last week kan you dah inform yang clash dengan miss. So dah okey lah. So tak perlu tukar balik ke?
Oh, tak ada. Yang Miss Yasmin tu tak ada clash dah.
So nak pukul 11 ke pukul 12 ni untuk
Selasa 11. Okey je, 11 sampai 1.
Hakim?
11 macam.
Okay, so kita eksperimen number 4. Okay, kejap. Because kan macam the PDF tu yang the PDF for each experiment tu kan, I think because you nak madam briefing ke ataupun tak perlu, because I think you boleh faham. Perlu ke tak? Sebab mostly madam akan baca je sebab it's not in my field. So basically kalau saya briefing tu is macam basic lah, very general one. Ke you nak madam brief?
Madam tak kisah pun. Kan madam, untuk start lab report kan kita ada data kan. Data tu untuk 10 lab report tu kita orang kena buat dekat lab lah dengan semua.
Ya. Tapi tengok dengan syarat apa tu, tools yang ada dekat lab tu yang mana berfungsi tu je lah yang you boleh buat demonstration. Kalau yang tak boleh tu maybe you can nanti technician akan update lah mana eksperimen mana yang you boleh buat. Kalau dia akan ada juga kat saya. Okay? Kalau yang tak ada, tak boleh tu, you can find resources tu daripada macam video tadi kan. Video yang saya share dalam e-learning tu, you report based on that one lah. Faham? Macam mungkin ada beberapa eksperimen yang you tak boleh buat. Nanti you finalize balik lah dengan technician kan. Then macam tu attach lah resources lah daripada which video atau mungkin ada dalam YouTube eksperimen yang lebih sama masukkan dalam. Tapi dengan syarat ni lah tools tu tak ada, maksudnya you tak boleh buat demonstration ni lah. So that one is okay. Tapi kalau lah for this experiment sebenarnya you boleh buat demonstration ataupun dah di dalam lab, tapi you ambil report tu daripada from ada video which is you tak buat untuk eksperimen. So tu tak boleh lah.
Okay, madam.
Okay. So madam go through eksperimen apa. Just very general lah, tapi madam tak adalah baca sebab I think Medium nak explain pun medium tak berapa family sangat. Okay, tapi saya just explain gitu-gitu je lah. Okay, experiment number 4 ni. Experiment number 4. Impact of jet. So this impact of jet using momentum equations. So the experiment is to verify the momentum equation experimentally through impact of jet experiments. Okay. So two objective, determine the force and then compare the result. So the compare result ni kena compare lah dengan actual value ataupun theoretical value. So for this momentum equation, that is the equation yang related to Newton's second law of motions that states the algebraic sum of external forces applied to control volume of fluid in any direction will be equal to the rate of change of momentum in that directions. Okay, so the external forces include the component of the weight of the fluid and the forces exerted externally upon the boundary surface of control volume. So the vertical water jet moving with velocity v made to strike a target which is free to move in vertical directions. Okay, so applying momentum equation in z directions, the force made by the jet against the surface is given by this equation. Okay, where v is the velocity of jet, which you can measure by q over a. And then we have for a flat surface whereby you have alpha that is equal to 90 degrees. The previous equation has the form of these new equations, Fv. Okay. This figure, flat plate. And for the curved surface, alpha is 120 degrees. Then you have Fy equations here. Okay. So figure something like this one lah. So alpha has 120 degrees. This is 120 degrees cone. Okay, for a semi-spherical surface whereby your alpha is 180 degree, then you have this equation of Fy. Okay. This is a figure lah to describe the surface. Okay, so the experimental setup can be seen in this figure 2 lah. Okay, so you have calibrated weight, flat, concave and spherical surface. Then you have adjustable support. And then here you have water tank. Okay, so you have a cylindrical tank lah for the setup with lateral transparent surfaces where a nozzle connected to the driving pipe of the bench is aligned with a device in which the problem surface is coupled. The vertical force made by the water against the surface is measured using calibrated weights lah. Okay, by this one. When the balance this force compared to a fixed indicator. Then the procedure, you have 6 procedures. Note down the relevant dimension as area of collecting tank and diameter of nozzle. When jet is not running, note down the positions of upper Ds. Okay, and then admit water supply to the nozzle. As the jet strikes the Ds move upward, and then place the weights to bring back the upper Ds to its original positions. At these positions, find out the discharge and record the weights placed above the Ds. Okay, and then repeat the process for different value of flow rate by reducing the water supply in steps. Okay, so for data collections, similar to experiment number 3, okay, you need to record your raw data and then show relevant graph. Okay, for example, relationship between your Fy and the W, or it can be relationship between Fy and the Fy with the experiment. So this is TH ni maksudnya theoretical value, macam true value, and then yang you punya from the demonstration is here lah. Okay, so you have what several graph, at least 2 graph lah. Okay, one graph is here, another second graph is here between these variables. Show the sample calculation because you are working with momentum equations kan, and then you have to show lah the computations, and then compare the value between your Fy dekat sini dengan Fy from the demonstrations. Okay, and then comment on the possible discrepancy between you punya theoretical and the demonstrations lah. Okay, and then provide some interpretations regarding how the object of the experiment was accomplished, and then provide some summary or conclusions. Okay, in terms of discrepancy tadi, you have to show lah what is the percentage of relative error that comes from the experiments. That comes from your experiments ataupun from you punya theoretical results. Okay, then as usual, and by put some suggestions lah to improve so that the experiment will get better results. Okay, so madam will play the video for experiment impact of jade, yeah.
Agak kecewa dan menyampah juga lah. Tengok muka sendiri.
Kesan jerawat kat sini tumbuh. Kalau jerawat saya hilang, saya akan sayang awak. 2 minggu tu hilang.
Saya sangatlah puas hati. Dah terbukti berkesan.
In hydropower plants, turbines are utilized to generate electricity. These turbines rotate due to reaction force produced when one or more water jets are directed tangentially onto vanes or buckets that are fastened to the rim or the turbine disc. The impact of the water on the vanes generates a torque on the wheel, causing it to rotate and generate electricity. The study of these reaction forces, which is the application of conservation of momentum principle, is an essential step in the subject of mechanics of fluids and hydraulic machinery. The objective of this experiment is to investigate the reaction forces produced by the change in momentum of a fluid flow as a jet of water striking a flat plate or curved surface, and compare the results with the computed momentum flow rate in the jets.
The apparatus for the study of a momentum of a fluid flow is the impact of jet apparatus. Water enters the cylinder vertically through a nozzle and then strikes a target mounted on a stem. A weighted pan mounted at the top of the stem allows the force of the water to be counterbalanced by applied masses. Water enters from the nozzle and after striking the target plate leaves through the outlet holes in the base of the cylinder. The vertical force on the target plate is measured by adding weights to the weight pan until the mark on the weight pan corresponds with the level gauge.
Remove the top plate and transparent cylinder from the equipment and check and record the exit diameter of the nozzle. Screw the 90-degree deflector onto the end of the shaft. Connect the inlet tube to the bench quick release connector. Replace the top plate on the transparent tank, but do not fit the 3 knurled nuts. Using the spirit level attached at the top, level the transparent tank by adjusting the feet. Replace the 3 knurled nuts, then tie in sequence to retain the top plate level indicated by the spirit level. Do not over-tighten the knurled nuts, as this will damage the top plate. The nut should only be tight enough to level the plate. With no weights on the weight pan, adjust the height of the level gauge until it aligns with the datum line on the weight pan. Check that the position is correct by gently oscillating the pan. Place a mass of about 50 grams on the weight pan and open the bench valve to produce a flow. Open the flow valve slowly and allow it to impinge upon the target until the datum line on the weight pan is level with the gauge and leave flow constant. Observe and note the flow behavior during the test. Now measure using the volumetric tank. This is achieved by closing the ball valve and measuring the time taken to accumulate a known volume of fluid in the tank, as measured from the sight glass. Repeat this procedure by adding an additional 50 grams each time until a maximum weight of 500 grams is reached. Then repeat the whole test section for each of the other flow deflectors. To change the target plate, undo the knurled screws on the top plate and remove this from the transparent tank. Take care not to over-tighten the knurled screws when replacing the top plate, as this can damage the plate. When finished taking readings, replace the deflector back to the first one used.
Be sure to clean up your station and any water that may have spilled. Following the lab manual, complete the results table and put together your lab report. If you have any questions, consult your teaching assistant or professor.
Okay, soalan tak for the experiment 4. Ada soalan? Lagi ke tak tu? Kau tidur dah tu?
Ada. Masih ada di sini.
Okay. Okay, so kita sambung eksperimen 5. So lepas habis eksperimen 5 ni, this is one part kan, fluid mechanics kan. Okay, so lepas tu kita review sikit lah on this part SOM. Okay. Sekejap saya check. Okay. Losses in part. Okay, losses part. Okay, experiment 5 last experiment under fluid mechanics lah. To verify one of the principle of fluid mechanics. Okay, basically is to observe the head losses in pipe flow due to the disturbance to pipe flow streamlines triggered by valves and such pipe fittings such as bands, sudden expansions and contractions. Okay, so there are two sub-objectives to determine the losses of a current that circulates through a short elbows of 90 degrees, middle elbow of 90 degrees, curve of 90 degrees, widening, narrowing, meter and membrane valve. Okay, and then last kali is to compare the result with the theoretical values. Okay, for this experiment number 5, energy loss in bands. Okay, so the energy balance between two points in a part can be described by equation 1. So this one actually is similar equation to the Bernoulli lah. Okay, with the meanings and so on. The head loss yang ni saya skip lah because this some of the item required lah. Okay, similar to the Bernoulli tadi. Cuma kat sini kita will have some additional level in terms of P1 and P2, V1 and V2 lah. Okay. So the head loss HL, label for head loss HL, includes the sum of pipe friction losses HF. So friction losses, sum of pipe friction losses HF and all minor losses is given by this equation number 3. Okay. HI is ni simbol hasil tambah Ni nampak this symbol yang saya highlight ni. This is hasil tambah symbol. HI is the minor head loss in meters for the I component and dekat sini there is an N kan, is the number of components. That means you punya number of components start daripada 1 sehingga N. Okay. So kalau you have 5 components, so that means you punya n is 5 lah, and so on. Okay, pipe friction losses are expressed by the Darcy-Weisbach equation. Macam ni, equation number 2. Kenapa ni nombor dia lain? Okay, saya rasa macam terbalik lah. So atas ni patut 2, bawah ni 3. Okay. Where F is the friction factor, L is the pipe length, D is the pipe diameter. Okay. The pipe friction losses are assumed to be negligible in this experiment. Okay. Maksudnya dekat sini pipe friction losses akan dianggap diabaikan. Okay, maksudnya. Ini maksud dia lah, to be negligible. So means that you boleh assume kita akan just abaikan dia punya pipe friction losses. Okay, minor losses occur at any bend transitions or fitting where the streamlines are not straight and are proportional to the velocity head. So the head loss is given by equation number, this should be equation number 4 lah. Okay, by this equation. So the fourth equation dekat sini is Ki, maksud dia adalah loss coefficient for the I component. V is the fluid velocity. Sometimes V also used in equation number 4. This is equation number 4. Meaning that it is the velocity of the fluid in the smaller diameter pipe. So in this experiment number 5, the loss coefficient for different pipe components will be determined by computing the minor head loss, equation 1 dan equation 4. Okay, so dalam you punya lab report, you have to show lah how do you get the value using these two equations lah, equation 1 and equation 4. Sini equation 4 bukan equation 5. Okay, so the setup you can see as shown in figure number 2. So we have this figure 2 show us the energy losses apparatus. We have the apparatus of local load losses comprised of hydraulic circuits with a set of elements that disrupt the normal flow of the fluid which circulates by the pipe because of sudden sections and direction variation as well as frictions. Okay, so we have several elements lah, okay, regarding this one, because tadi saya ada mention lah about this kind of situations. Okay, so from figure 2, what we have, the equipment has 2 manometers, modern type, okay, then 0 to 2.5 bar and 12 manometric pipes of pressurized water. So the system is carried out regarding the pressurization is carried out with a manual A pump. The hydraulic circuit has pressure takings along the whole system, which enables to measure the local load losses in the system. Then the system also has 2 membranes valves, a valve which enables the regulation of the outlet flow, and a valve placed in series with the rest of accessories of the hydraulic circuits. Okay, so these are the detail of the procedure. Assemble all the equipments and then connect the input tube from the equipment to the pulse mouth of the bench, and then fill the manometric pipes with water, and then check once the system is pressurized. Turn on the pump and open gradually the control valve and slightly the valve of the bench of group BC while you open gradually the control valve of the equipment. Make sure that the procedure carried out in a very softly way to avoid the measurements are out of the scale. Okay, so procedure number 5 ataupun step number 5 is an important one. Okay, next, regulate the flow with the control valve of the equipment. Okay, when the valve of the bench or group is completely open. Okay, next, record the readings. Okay, based on your several different situations, and then check the water flow, record all important numbers, and then close the control valve of the bench. Repeat the steps, varying the flow by opening the control valve of the equipment, and then make sure all data that you're supposed to show in data collections or raw data are recorded in data logging sheets. Okay, so similar to previous experiments that I have mentioned, all the important raw data and items should be recorded and show your results regarding relationship between variables. Okay, so for example, relationship between you punya change of H and the V squared, okay, and the K value. So in this data, you have to show calculations. How do you get the K using which equation and so on lah. Compare the data obtained, and compare means that maybe you can compare between the recorded or the actual one, and then provide some recommendations or justifications when you have possible discrepancy. Okay, and provide a summary of conclusions lah. Okay, include you punya interpretations, explaining how the object of the experiment was accomplished. For example, you can provide answers whether the static pressure increase or decrease, okay, for the enlargement and contractions. Okay, and then provide evidence regarding you punya percentage of relative error. Okay, and then end by you punya suggestion of increment, how we can get better results. Okay, for experiment number 5, let's see the video.
How do you say, Dior? Dior
Sorry.
addict, delectable, divine. Ooh la 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 la.
Hari Raya is a joyful time, made precious Ferrero Rocher. Make every celebration a golden one. Ferrero Rocher.
Hello everyone, this is the last part of our lab 8, which is also our last lab for our Introduction to Fluid Mechanics ENGR 3404. So in our last part of the lab 8 in B, we're going to study the energy losses in bends, which is also a minor head loss. So let's see what is our learning objective for today. So we're going to investigate the head loss in fittings. So for example, in this equipment you have long bends, enlargement, contraction, small bends, and then you have miter bend, and you have gate valve. So this kind of fittings can cause head loss, and these are the minor head loss. So we're going to investigate the minor head loss in those fittings. Now, through that, we're going to determine the head loss coefficient for minor head loss. And finally, we're going to investigate the relationship between head loss coefficient, which is K, and the volumetric flow rate, Q. And again, head loss and flow rate, which is V, velocity. So, let's take a brief moment to cover the theory. The head loss in pipe fittings are defined is that del H, so it's in meter. K is your head loss coefficient, which will be different for every different types of fittings, and velocity is the flow of entire pipe. So we can find the velocity if we can collect the water flow at the end over a certain period of time, and then if we know the cross-sectional area. So again, just a quick recap of how do we measure the head loss, del H, in our system. If you remember, on our lab 8A, our pipe was smooth and the diameter was fixed. And now in this case, in the pipe fittings, there will be contraction and enlargement. So there is change in diameter. That means there will be change in velocity. And that's why the equation will be a little bit different from section to section. So again, if we apply the Bernoulli's equation, for example, in this case, if you see here, this is the inlet of the long bend and this is the outlet. Here, the diameter of the pipe doesn't change. If it doesn't change, we still stick with the same concept. Del H would be only the change in pressure. This doesn't exist because there is no change in velocity within this length of the pipe because there is no change in diameter. So this will not exist for when there is no change in diameter. So for a calculation of this one, we can just get the pressure head if we know the head loss, if we know the pressure difference using the manometer. Now for section like this, if you see here, this is the original diameter of the pipe and this is thicker, so there is an enlargement. And if there is an enlargement, there will be change in velocity. So only the change we'll have, then we cannot say the V1 equals to V2, we cannot say that. And if we neglect the elevation, we can write the del A should be the pressure difference, also the kinematic pressure difference. And how can we find the V1 and V2? So again, for the contraction and enlargement, we have to, after we take the manometer reading, we have to balance doing this, adding with the pressure difference that we find. And to find this, we need to know the velocity. How do we find that? If we collect the total water flow, and if we know the cross section of this contraction and enlargement cross section, we can find those velocity. So by contraction, what I mean is that from contraction, you're gonna go to enlargement. So a small diameter, you are at contraction, so you are at minimum diameter, and you're going to the enlargement. In that case, your velocity will be higher in this region, and velocity will be lower at the enlargement region. On the other hand, when you are in the enlargement section and you're going to the contraction section here, your velocity will be, whatever velocity you have, the velocity at the contraction region will be smaller. So let's move forward. Okay, so Reynolds number. Again, for this type of flow, we also can find the Reynolds number using the same theory that we have covered for the lab 8A. We know the water density. If we take the water temperature, we can find this mu, and then kinematic viscosity. We can also find it. If we just know this one, we can find this one easily. And diameter is given for the pipes, and velocity we can collect the water and divide it by the cross-sectional area, so we can find the Reynolds number. So the Reynolds number for this lab will be used to determine whether your flow was turbulent or laminar. So let us introduce ourselves with our equipment. So this is the setup for our minor head loss due to flow through pipe fittings. So what we have here is that we have a pipe system. It has a lot of fittings here. We have a long bend here. From here, you see, from here to there's a thickness change. So this is the area enlargement. And from here, if you see from here to here is a diameter change. It gets smaller. So there is area contraction. And we have a small bend. We have an elbow bend here. We have a gate valve. And we have a miter bend here. So what we're trying to do is that we're trying to measure what is the head loss when the water flows through these fittings, these bends. So how it is connected is that, if we want to measure, for example, what is the head loss when there is an area enlargement. So from here to there is a change in diameter, so area enlargement. What is the head loss over there? So what you have to do, you have to take the pressure at the low diameter or actual diameter. So that is this diameter pressure. This pipe is going to reading that pressure. and then there will be another pipe that is coming out after the enlargement. So if we can connect these two, so this is the enlargement reading on the manometer. So you see one is connected after the enlargement, and the other one here is connected before the enlargement. So this is how we're going to measure the differences in the manometer, and this is how we're going to measure the head loss for each feedings. Same for example, this elbow, this small bend will have one outlet after the elbow and then one would be before, and if we can differentiate between two pipes, 2 manometers, and we can measure the head loss. For the gate valve itself, we have the gauge here, and we're going to use this gauge reading. So this is the top part of the manometer here. We have one here is air bleed screw. What it does is that if you open it, it lets the air into the manometer, and then water will fall down. So we'll keep it closed. And here we have air connector. What I'm doing is that I'm opening the air connector. There's a cap on the screw. So I open it, and I'm connecting a hand pump over there. This will be needed if the water is too high, and then I cannot take any reading. So if I need to lower the water head, I can push some air into the top part of the manometer, and the water will come down, and I can take the reading. So I'm connecting the hand pump. You see, it will let some air in. See, the water level is going down with that pump. So if we need it, we'll do it, but for now I'll just close it. All my manometer inlets and outlets are open. All of these valves are open. Now I can turn on the pump to take our test data. So for this test, we're going to do the data collection in 2 stages. First, we'll keep this valve fully open, and we'll measure the manometer reading for each of those. I'm going to show you a little bit. We have names, which manometer is going to give us which reading. You can also look at the pipes and also know where it is coming from. So that will be the first stage. On the second stage, we will not going to use this manometer. We'll close the manometer outlets, and we'll use this gauge reading for the gate valve friction gate valve minor head loss. So first part, we're going to use entire feedings except this one, and then for the second time, we're going to just use this one. So the data collection for the minor head loss in pipe feedings, we have to know the diameter of the entire system was 0.018 meter. Only where there is enlargement, that diameter is 0.024 meter. We can take the water temperature, and what we have to do is that for all those changes, that there's a contraction, there's enlargement in the system, short bend, long bend, elbow, and matter, we have to take the manometer reading, H1 and H2. This will be H2. Then we can measure the head loss by taking the difference. You have to collect the volume of water over a certain period of time. That will give you the flow rate, and from the flow rate, with the cross-sectional area, you can find the velocity, and you can find the kinematic head. And from the theoretical equation that we just discussed, you can find your coefficient of head loss for each of those feedings. There will be different K, and then you can also find the Reynolds number, whether the flow was laminar or turbulent toward the system or different, and where the change or the change in Reynolds number on those feedings. So I have turned on the pump. There is no water flow. I am slowly opening the pump. Slowly. You see the manometer reading is going up. All the manometer is being filled with water. So the pump is running. There is no air bubble into our manometer. It is totally filled with water. Now we have to lower or control the bench valve from the pump so that the water flow rate into the pipe is no more than 70 liter per minute. We have to do that because if we have more water flow, the pressure will be high and we will not be able to take reading using this manometer. So we have to keep the water flow up to a certain limit so that we can take the reading. Now it is totally full, so we cannot take the reading. So we have to lower the flow rate below or at 70 liter per minute. So how do we do that? We're going to keep reducing the flow rate through the bench valve gate, and we're going to measure the water collection over there, and from there, given a time, what is the volume of the water? If we can divide that, we can collect what is the flow rate, and from there we can measure whether it is below 17 or not. So I'm going to lock this outflow. Now water is going to go high up on this meter in your bench valve here. So on this reading, I'm going to use this reading using a time. So I'm going to measure how much water filled up given a time, and I can measure the flow rate. So the pump is running, the water is going up. My goal is to have no more than 70 liter per minute. So what I'm going to do is that when I have a mark, for example, now it's 2 liter, I'm going to start. And what I'm going to take is that how much time it takes to fill 5 liters. So it was here, 1, 2, 3. So how much it will take to be at 7 liters. If I can get 7 liters in 20 minutes, then I will have about 15 liters per minute. So I will be well below the range of 17. So I'll be good to go. So I'm only 22 seconds and I'm about 17, so I am good to go. So once I know that my flow rate is below 17 liter per minute, now the data collection is very easy. For this case, you see the water level on the manometers are below within the range, and if the water level is way up, you can open the air bleed valve to get some air in. If it doesn't work, then you can pump some air, but in this case I don't have to because they are well below the limit. So now you see it has the tag enlargement, contract, long. There is long elbow here, short elbow, elbow here, and wider elbow over here. The valve is fully open. So all I have to take is take the reading between these two. So you see, if you take the reading between these two, sometimes you will see the water level is dropping. What you can do is take a picture of an instant and take the differences. So all you have to collect is the head difference, maybe H1 and H2, and take the difference at any instant. And then you will take the data for all those losses. Next, what you have to do is just change the flow, maybe lower a little bit, maybe up to 10 liter per minute or 12 liter per minute. Take a different flow rate between 8 to 17. It has to be between that flow rate, and take data point, take the minor head losses.
สวัสดีค่ะนุชนะคะ วันนี้เราอยู่กับคุณเอยจากอายิโนโมโตะสวัสดีค่ะ วันนี้คุณเอยจะถึงโครงการเพื่อความยั่งยืนของบริษัทให้เราฟังไร่มันสำปะหลังแห่งนี้นะคะ
Okay, ada soalan tak for the experiment number 5?
Tak ada kat mana Pak.
Okay, so untuk yang semua eksperimen bahagian fluid mechanics ni, okay, kena submit lah before 3rd of May. Saya dah tuliskan submit experiments 1 until 5 before 3rd of May. Okay. So that means kena ada ni lah 5 report lah for each of these experiments. So setiap submission kena attach together the rubric lab report evaluation.
But Madam, since tak ada data, macam mana kita orang nak proceed lab report
Macam mana?
Since kita orang balik pun on maybe 2 Mei ataupun 1st Mei. So macam mana nak buat lab report kalau tak ada data?
Kalau boleh balik awal sikit lah. Because saya beritahu kan, try lepas macam next week tu datang sampai okay. Kalau you dapat hantar 3 daripada 5 tu pun be okay lah. Okay. Confirm balik, confirm dulu dengan technician because saya tak dapat lagi you punya schedule sebab saya minta hari tu I think last week kot confirm balik dengan saya schedule because saya nak prepare attendance dalam e-learning. So by esok bagi tahu saya lah bila you punya schedule dengan technician. Boleh kan? Okay, soalan tak?
Soalan dia mana?
Tak ada.